If you care about LLM agents, this is worth watching because the bottleneck may not be the model anymore. NVIDIA's ProRL Agent is aimed at a practical problem in reinforcement learning for multi-turn agents. The rollout side and the training side want very different machines, timing, and software. Rollouts spend time waiting on tools, sandboxes, shells, and environment responses. Training wants steady GPU-heavy policy updates. Put both in one tightly coupled loop, and one side slows the other down. That is the core claim here. ProRL Agent tries to separate those jobs into a service layer for rollouts and a trainer that only talks through an API. So the real question is not whether NVIDIA has a new benchmark number. It is whether this system design removes unknown infrastructure drag on Agent RL, especially as tasks get longer and more tool-dependent. The source points to a pattern across existing frameworks like SkyRL, VRL2, Agent Lightning, RLLM, and GM. In many of them, rollout control sits inside the training process. That sounds neat on paper, but it creates two predictable issues. First, the system requirements conflict. Multi-turn agent rollouts are I/O bound. They need sandbox creation, long-lived tool sessions, and asynchronous coordination with external environments like code repos or operating systems. Training is different. It is dominated by forward passes, backward passes, and gradient synchronization on GPS. Second, maintenance gets harder. If the rollout logic is buried inside the trainer, moving to another back-end or runtime means redoing the execution pipeline. NVIDIA's framing is that Agent RL has outgrown that setup. As agents become more realistic and tool-heavy, the infrastructure itself starts to decide how much learning you can actually afford to run. ProRL Agent treats rollout as a standalone HTTP service. That is the architectural move. The trainer no longer manages the full agent loop directly. It calls an API and stays mostly agnostic to the rollout machinery behind it. Inside the service, NVIDIA describes an asynchronous three-stage assembly line. init workers prepares nbox containers and tools. RUN workers execute the multi-turn agent loop and collect trajectories. EAL workers score outcomes against ground truth and produce reward signals. The practical benefit is overlap. So evaluations, like running a full test suite, do not have to stall the whole system. Different jobs can sit in different stages at the same time. This is a product-aware design choice more than an algorithmic one. It says the path to better RL throughput may be to specialize each stage, parallelize them independently, and stop forcing rollout orchestration to live inside the trainer's timing constraints. A lot of the value here sits in details that are easy to miss. ProRL Agent uses singularity rather than Docker, force, and bracking, mainly because rootless execution matters on shared HPC clusters managed by SWE-Bench. That makes the system easier to deploy in real research compute environments. NVIDIA also reports latency cuts in the tool layer. It replaces TMUX-based shell handling with a PTY process direct pseudo-terminal, dropping shellcom and latency from 0.78 seconds to 0.42 seconds. It connects to persistent IPython kernels through an in-process API instead of network gateways. It also swaps TCP loopback for Unix domain sockets inside the container. On the inference side, the server manages backend pools such as VLLM and keeps a task pinned to one backend to reuse prefix cache across turns. And To avoid tokenization drift, token IDs remain the canonical representation from rollout to trainer. The clearest signal is architectural. ProRL Agent appears to improve throughput by separating I/O-heavy rollout work from GPU-heavy training and by reducing avoidable execution overhead inside the loop. The source also reports benchmark gains on SWE-Bench verified with Q, when 3 models 8B rising from 9.6% to 18.0%, and 14B from 15.4% to 23.6%. Alongside near-linear rollout throughput scaling as compute nodes increase. Those are meaningful numbers, but they should be read in context. This is not proof that decoupled rollout solves agent are ill in general. It is evidence that infrastructure design can materially affect training efficiency and final performance until using tasks. It also showed reward growth in STEM, math, and code settings, which suggests some generality. Still, the enduring takeaway is narrower and stronger if you are training multi-kernel LM agents. The system boundary between rollout and training may matter almost as much as the optimizer.